Hey guys, I wanted to talk a little bit about microphones today, specifically measurement microphones or lab measurement microphones, which are quite different from your standard run-of-the-mill either recording microphone or obviously different than what you would put in a product. This is what they look like. So this is a proper measurement microphone. There are a few different varieties, and I'll get into the different types of measurement microphones and why you need them. So let's just take a quick look at the anatomy of one of these things. This is the preamp, which really isn't really an amplifier, but it keeps the signal at the same level, but buffers it, I believe. Gets power from that end. The microphone gets biased. There are some microphones require 200 volt bias, other ones are pre-biased. We don't have to worry too much about that at the moment. So basically this is the microphone capsule that you buy. This is, this kind of has to go along with it, and you also need a power supply which goes to the other end of this cable. But I'll show you that stuff shortly. This is the business end of the microphone. Usually with these lab microphones, you might find the markings on the outside, or often you'll find them in here, depending on the maker. Usually B&K and GRAS, GRAS are the two big vendors. This one is actually an ACO Pacific microphone, as you can see. A lot of glare there, but there you go, ACO Pacific. They're less expensive than B&K. But then so is everybody. But B&K are super reliable and super robust, and so you get what you pay for. Now this is called the grid. What you see here, this this is really two parts. There's the microphone part, and then there's the grid. Generally don't unscrew these, but oh, that one's really kind of on there tight. Maybe I guess I won't unscrew that. I was going to unscrew that for the video to show you the diaphragm, but anyway, you can't get in there. There's a stretched and tensioned diaphragm inside here, they're really built, to be utterly impervious to the environment. Humidity in the air, temperature, they just don't change over time. So you can be sure that a year from now, 10 years from now, that this will keep measuring the same without changing. You do want to get them calibrated once in a while to make sure that it hasn't gotten broken, but as long as it hasn't gotten broken, it should pretty much be the same thing for a long time. Okay, so this is a 1/2 inch pressure field microphone. Here is a 1/4 inch free field microphone. You can see there's sort of a similar kind of setup here. There's a little microphone capsule itself. These things are expensive, this will be $1,000, something like that. And this is just an adapter, 1/2 inch to 1/4 inch adapter. Doesn't do much except that, and then similarly same preamp as before. That's how they go together. And then you might ask the question, why do we need a measurement microphone? Like, what do you care about? And the reason is that basically nothing else in your acoustic lab is reliable. You cannot rely on your loudspeakers, and you can't rely on sort of commercial grade, just regular microphones. These you can rely on. And let's take a look at the frequency response of this 1/4 inch microphone. So from when it was calibrated, which, don't look at the date, that was a long time ago and hasn't been calibrated since, but we can always get it calibrated if we want to get certified for anything. Each one of these lines is 1/2 dB, so you can see the frequency response of this 1/4 inch microphone here. This is 200 hertz, 100 hertz, 1 kilohertz, 20 kilohertz. So at 20 kilohertz, at 15 kilohertz, where it's deviating the most, it's deviating by like, what is that? A little more than half a dB, 3/4 of a dB. And then you can even keep using this meaningfully, reasonably well, all the way to, looks like 100, 150 kilohertz. So this 1/4-inch microphone is super flat frequency response for very extended frequency range, and also all the way down to 20 hertz. It's just dead flat. There's nothing. It only starts having a meaningful effect way up high. So, yeah. So this is why you get a measurement mic. It's just perfect. It's perfect always. It's perfect all the time, as long as you use it right. I did mention that there are two kinds, that I have two different types of microphones. They're both 1/4-inch and 1/2 inch. Fundamentally, there's no difference. The trade-off between sizes is 1/2 inches microphones are way more sensitive, so they have a much better noise floor. 1/4-inch microphones have way higher noise floor, so they're not great for doing certain measurements like very fine THD kind of measurements and that kind of stuff. But what they are really good for is they're quite immune to shall we say, like placing it at a sort of a different angle. They're robust in that sense, so you could you can use it in your system. Both you can pretty much use this as a pressure field microphone, even though it's really a free field microphone. You might ask, well, what does that mean? What's a pressure field versus a free field microphone? And you can go on B&K and look up the different microphones, and they're really for use in different use cases. Free field microphone. There's a microphone, wire coming out of it. Free field microphones are meant to be used basically in open space with the sound, impinging on it like that. And all around here, there's nothing surrounding it, so sound can just flow right past it. So all the sound waves hit there and go past. Whereas a pressure field microphone is meant to be embedded in essentially, a pressure field. So this might be a wall, and let's see. And the sound is coming in and impinging on here and then bouncing back. So, the sound bounces back off of this baffle, and that's where pressure field microphones are used. They might be used inside a chamber. Let's say you've got some kind of test chamber. And you got your microphone embedded in the test chamber. So typically this kind of setup, you've got, a loudspeaker here. You have your little loudspeaker there driving into this chamber is whatever, it's some kind of test. And you want to measure the sound pressure in this chamber. You use a pressure field mic. This one is a pressure field mic, so you just stick that there in your box and play. And that's when you want to measure stuff in open space, you use your free field microphone in open space. And basically the reason for that is, if you imagine when sound comes up against a wall here, and so you've got your wall and infinitely big wall, and you have some kind of sound source here, maybe a little speaker making sound. When the sound waves hit here, let's say if we're drawing them like this, they bounce off, and as they bounce off, right at this boundary here, the pressure doubles. So if you have an infinitely big wall, anywhere along this wall, you'll get double the sound pressure, which is 6 dB more loudness right at the wall. If this wall is not infinitely big, right, so you imagine you actually have a corner. So sound is coming in this way. Some sound is going to be able to just continue on, right? And this actually kind of re-radiates there a bit. And some reflects back. So you're not going to get that full 6 dB of boost. So this actually starts to matter with measurement microphones because sound waves at 20 hertz are really long. You know, I forget how long, 50 meters or something. You know, we can figure that out easily just with the speed of sound. But at 20 kilohertz, it's actually quite small. The wavelengths can be, you know, as small or smaller than, you know, in the ballpark of size of this half-inch microphone. So what that means is for very high frequencies, this is your measurement microphone. You know, we've got measurement microphone and the little grill there. As sound comes along here, and let's say it's sound from far away that's coming in essentially parallel, right at the center of this diaphragm, you can get nearly a doubling in sound pressure, but at the edges, it won't be nearly double. So at high frequencies, it actually behaves, and at low frequencies, the sound will just go past this microphone without even noticing the microphone's there at all. There will be no doubling of sound pressure with really long wavelengths. With really short wavelengths, you actually get a sound pressure that, you know, goes across this diaphragm. You'll get, turn it this way, you'll get, you know, some amount of sound pressure at low frequencies at the edge, like right here, and it'll actually boost up and go down, you know, so there'll be lower pressure here, higher pressure there, lower pressure there. And that is, that's one of the effects that happens when you're sort of in the free field as opposed to a perfectly even field. Anyway, so what's the practical reason? Practical issue there is that you essentially want to use different types of microphones for different measurement environments. It's simple as that. So let's take a look and see what the effect really is. So what we're going to do is we're going to set up a loudspeaker. That's my beautiful loudspeaker drawing. And we'll go 10 centimeters to the measurement microphone. And then we'll measure that. Because remember, you can't rely on loudspeakers at all. So this is going to be a terribly non-flat frequency response, but that'll be our reference. We know that at 10 centimeters from the face of the speaker, we'll know exactly what the sound pressure is right there. And this 1/4-inch mic will do a great job of that. Then we can try things like what happens if we turn the mic 90 degrees? Are we going to get a different result? What about a pressure field mic in that same field? What's the difference? What if we turn that 90 degrees? And what if we use a so-called measurement microphone from Behringer? That's one of these things that looks vaguely like a measurement microphone, except if you look carefully up here, I don't think this thing untwists. It's even, yeah, doesn't look like it. It's just got a ECM microphone there. Condenser mic, you know, that's like a 10-cent microphone. You know, what's it gonna be? I suspect not as good as the $1,000 microphone. we can take a look. Okay, so here's our test setup. We've got a loudspeaker and our measurement microphone, and this should be 10 centimeters. Let's get that about right. And there we go. So you can see we're set up for 10 centimeters from the face of the loudspeaker, and then we'll do a frequency response measurement. Okay, here we go. We have our first measurement. Remember, this is measured with our 1/4 inch microphone that's nearly perfect. So this is entirely the frequency response of the loudspeaker itself. So you can see loudspeaker, they can only produce sound. That was a small loudspeaker, so that's 200 hertz. It really starts losing what it can produce. At higher frequencies, it's got, as you can see, a few little bumps and ripples, and this is going to be our 0. This is going to be our reference for all of the future measurements, and we will normalize the other measurements of the microphones to this curve, and also make 1 kilohertz be 0 dB, so that we can just easily compare all the measurements. So what we're going to do is we can now take this mic and move it so that it's, let's try 90 degrees. So we'll get 90 degrees off axis, and again 10 centimeters away. Okay. Okay, so here's our normalized pressure-free field microphone. This is our reference microphone in our reference world. So it's perfectly flat as expected. Now, as we add, that is our microphone, the same microphone, same free field 1/4 inch microphone, but recorded at 90 degrees off axis. Our measurement setup in my lab here is not great below 100 hertz, so you can pretty much ignore this stuff. You see there aren't many data points, but more importantly, there are reflections. That's a whole other topic that I'm not going to talk about today. Also, these ripples are also a measurement artifact. Those are not real, I'm pretty sure. I could verify that, but again, won't worry about that for today. But the main thing to look at is to see the 1/4 inch microphone is really quite good. It's losing a dB or so at 7 or 8 kilohertz when it's 90 degrees off. It's still pretty good, and doesn't start really falling off until after 10 kilohertz. At 20 kilohertz, we're minus 4 dB. So yeah, it does matter. You do want to point your microphone in the direction that that you're measuring from, and this shows you what happens if you're 90 degrees off. Okay, now let's try the pressure field mic. When I'm winding these things off, I always go unwind, then wind a little bit. Unwind, and eventually it pops off. The reason I always do that little bit of extra wind back on is so that if we're just at the end of the threads, it doesn't fall off onto the floor. Okay, there we go. Again, let's hit 10 centimeters. Well, we want to try this position first. Okay, there we go. Now we get to add the pressure field microphone at 10 centimeters. And you see that's really pretty good. Let me get rid of this, get rid of that one. You see it's actually quite good up to, you know, 8 kilohertz. Then really starts losing it. Yeah, still, again, it's 2 dB here, so yeah, that's not great. You don't want any sharp, you see how that's a pretty sharp transition there. You don't really want that in a measurement microphone. So if you're only doing measurements up to 8 kilohertz, this is perfectly good. Again, these ripples are a measurement artifact. Don't worry about those. But this is for real. Yeah, that's definitely for real there. So yeah, you can use a pressure field as a free field microphone up to 8 kilohertz. And that's about it. That's when you're pointing the microphone at the source. Now, next up is what happens when we turn it 90 degrees. And we'll try 90 degrees. Okay, so at 90 degrees, nope, that one. So again, this is our pressure field at 90 degrees, and it really starts losing its energy there. You can see, again, it's good up to, let's see, 10, 9, 8, 7 kilohertz, perfectly good. 8 kilohertz, you're down 2 dB, yeah, that's starting to lose it for sure. After that, forget it, you know. So yeah, so the pressure, half-inch pressure field definitely has a very different effect from the at 90 degrees from the quarter inch at 90 degrees. Remember, that's our quarter inch at 90 degrees. It holds up much better, well past 10 kilohertz. So that's why quarter inches are a little bit better for doing frequency response measurements, but not nearly as good for doing distortion measurements because of their noise floor. And finally, the Behringer microphone. We'll see how that does. And here comes our Behringer microphone at 0 degrees head on. Again, we can ignore this, but this is a major concern. That means this thing's essentially useless as a measurement microphone. You can calibrate to it. Like if you have a good measurement microphone, you can calibrate this thing and you can add this curve in to your measurement software. But even here, like look at this transition, this sharp resonant peak here. Those resonant peaks shift a lot over time and temperature and everything. So if something has a non-smooth frequency response, it's really not good as a measurement artifact, measurement device, sorry. Now on the other hand, this is probably a $50 microphone, this Behringer microphone, and the measurement microphone, the proper ones are, you know, very expensive. They're $1,000, $2,000. So, you know, it's a trade-off. And finally, here's the Behringer at 90 degrees. And there we go. It's strangely, it's a little bit better, but yeah, you still have this really pretty horrible peak at 10 kilohertz. You would never want to actually measure anything with a microphone that has a behavior like this. Yeah, it's just not a good plan. So there you have it. Here we can zip through. Let's see, we've got our perfect microphone. Perfect microphone at 90 degrees. Pressure field microphone at 0 degrees. Pressure field microphone at 90 degrees. Cheapo microphone
and cheapo microphone at 90 degrees. And yeah, there you have it. Buy a good microphone. You only need one for your lab. You probably need more than one depending on what you want to measure, but a single 1/4 inch microphone can get you a long way to doing just about any measurement you want to do. You may need a 1/2 inch for distortion, so maybe 2 microphones. Anyway, thanks for watching.